Today we're going to look at the periodic table, and in particular I want to explain to you why the periodic table that I sell on my website, which I call the alternative periodic table, looks a bit different from the one that you're used to seeing. So let's go back to that one. This is a traditional or standard periodic table, and it has this unique shape that most people will recognize, even if they don't know much about chemistry. In fact, the periodic table is probably one of the most well-known and most recognized charts in the world and hangs in many classrooms. But why is it shaped like this? Unless you got an A in chemistry, most people would probably struggle to explain that. But that is what I'm going to try to do in the next few minutes, is explain why the periodic table is shaped like this, and why it doesn't have to be, why we could arrange it slightly differently. So the first thing we'll point out here is the atomic numbers. You can see each element has a number in the top left corner. This is called the atomic number, and basically it indicates how many protons are in that particular atom. So an oxygen atom has 8 protons, whereas a nitrogen atom has 7 protons. Now, generally speaking, this number also equals the number of electrons that spin around the nucleus. Now, if you're already confused, let's take a quick look at what an atom looks like. Now, an atom doesn't look actually exactly like this. This is just a model called the Bohr model. So we have a nucleus here in the middle, which has the protons, and then the electrons spin around the nucleus. And you can see here that they also start to group together into different shells. And here we have 7 different shells. Okay, so protons in the middle, electrons spinning around. Let's go back to the periodic table. So if we take a carbon atom, we can imagine 6 protons in the middle and 6 electrons spinning around. Now, the reason why this whole thing is called a periodic table is because of these numbers over here. These numbers represent the period. So the first row of the periodic table represents the first period. The second row, second period. Third row, third period, and so forth. So what the period number represents is the number of electron shells in that particular atom. So if we take the element neon, it is in the second period. Therefore, we know that a neon atom has 2 electron shells, whereas krypton, yes, there's an element called krypton, Superman would be proud, is in period 4, and therefore we know that krypton has 4 electron shells. So you'll notice that not every period has the same number of elements. The first period only has 2. The second period has 8. The third period also has 8. But when we get to period 4, we now have 18 elements. And period 5 has 18 elements as well. Now, the reason for this is as atoms get larger, we get more room opening up on the various electron shell levels, and so therefore we can fit in more elements before we have to add a new shell. Now, at this point, I should probably explain what's going on here. These elements at the bottom of a periodic table are kind of like a footnote. They're actually meant to be squeezed in here. And if we did that, the periodic table would actually look like this. And this is how the periodic table is supposed to look, because when we get to period 6, there are actually 32 elements in this period. So those are the periods or rows. What about the columns? The columns of a periodic table are called groups, and here elements are grouped together according to how many electrons are in their outer shell. And this is important for chemists for knowing which elements can be combined together to create various compounds. So the overall goal of the periodic table is to arrange the elements into periods and groups so that they line up according to how many electron shells they have, and then they also line up according to how many electrons in their outer shell. Now, if we look at the very first periodic table, this was the original periodic table. You can see here how it's arranged into groups and periods. Slightly different, but the principle was basically the same. And so this is why every periodic table that has come after that tries to do the same thing. Now, there are different ways to do it, though, and so I want to show you some alternative periodic tables. The most important one is one that was made in 1929 by a man named Jeannette. I believe he was French. And basically he said, well, why don't we just align everything over here to the right, and then as the periods get bigger, things kind of stretch out here toward the left, but we still get to keep everything into nice, neat columns as groups. This didn't really catch on, but it's been used by others to create some other possible alternatives. Here's an alternative periodic table, which basically takes Jeannette's table and flips it around and turns it on its side, so that we start down here 1, 2, 3, 4, 5, 6, 7, 8, and you can see how the periods get bigger as well this way. Here's another one, which is basically the same thing, but here they've kind of center aligned it so it looks kind of pretty, but as we read the chart we kind of have to angle through to get the periods. And then we get this nice rainbow one, which kind of follows a similar principle, except for we read it here from left to right. But then these colors represent the groups and how to keep those together. And then we get these really neat circular ones. This is from a Life magazine cover in 1949. And here you can see someone decided to make it kind of circular and spiral. And as the circle goes around, it gets bigger because the periods get longer. And then here's another one. Again, we start here, and as we spin around, the periods get bigger, and then we have to add this little part here. Another similar design here. So these are all different ways to display the periodic table of elements. I like this one. Not sure that I fully understand it, but it certainly looks neat. This one's called the Mayan periodic table because it kind of looks like the Mayan calendar. So you can see as the periods get bigger, they have more elements in them. It doesn't have to be circular. Here someone's made a periodic table with triangles, and here's one with hexagons, and here's one that's divided into various quadrants. And then some people have decided to make a 3D version in order to explain the elements and how they come together into the table. Here's another three-dimensional one, and a final three-dimensional one. So as you can see, this is not the only way to display the elements. There have been a lot of different ways that people have tried to do it over the years. Now, to explain the design choice that I made, I have to point out one more aspect of the periodic table that we haven't mentioned up to this point. So we talked about the rows, which are the periods, which represent the number of electron shells. And we talked about the columns, which are called groups, which represent how many electrons are in the outer shell. But there's also something called a block. And if we look at this next image, you'll see that the periodic table can be divided into 4 blocks. And without going into too much technical detail, you'll just notice the first period only has one type of block, but the second and third periods have 2 types of blocks. And then the fourth and fifth, we get 3 different types of blocks. And the 6th and 7th periods have 4 different types of blocks, because this section here, again, is supposed to be squeezed in here. And what these blocks represent are the subshells that exist within each electron shell. So for example, the 4th electron shell, once an atom gets large enough, can actually be divided into 3 subshells. So there's a subshell that has only 2 electrons, there's a subshell with 10, and then there's a subshell with 6. So what would happen if we started at the top and just started listing out the elements, but then every time we hit a new block or we hit a new period, we started a new row instead of putting them together like this? Okay, so that is actually what I've done in my alternative periodic table, and it ends up looking like this. So instead of each period having its own row, I've grouped the periods together into sections like here. So you can still see 1, 2, 3, 4, 5, 6, 7 periods. But every time the block changes, we get a new row. So you can look up here. Here is the original, the traditional periodic table. So elements 1 and 2 are here to make period 1. Period 2, which has 8 elements, we get 3 and 4 here, but because 5 starts a new block, we're going to put it underneath. And period 3 looks very similar. But period 4, we're going to get this green block here. So we've arranged it like this: 2, 10, and 6. Period 5 looks the same. And then period 6 and 7 are the largest because they have these large blocks here, which normally are at the bottom of the periodic table. But this way it actually keeps the elements in order, and you can read quite easily top to bottom, left to right. And it also shows that those ones that are normally at the bottom, actually they have elements that come after them. So this idea was not actually my own. Someone else made a very similar periodic table several decades ago, a man named Edward Mazurs, and it looked something like this. So I used that as a basis for my own design, changed the colors and added some extra information in. So this alternative periodic table can still be used like a normal periodic table. You've got the atomic symbol here and the atomic number, the name of the element, the weight up here. But I've also put the electron arrangement. So here, this is a period 3 element. So it has 3 electron shells. The first one has 2 electrons. The second one has 8. And the last one has 2. So if we add 2, 8, 2 together, we get 12. And if you want to see how that further breaks down into subshells, you can look over here and you can see that first shell has only 1 subshell with 2 electrons. The second one, though, although it has 8 electrons, is divided into 2 shells, one with 2 and one with 6. We also have these symbols here, which represent the state of matter at standard temperature and pressure. So the circles are for gases. There's only a couple that are liquid. That's shown here by a triangle. Most elements are solids. In fact, most are metals. If there's no symbol at all, that means they're a metal. If there's a filled-in square, that's a non-metal solid, and a square like this means it's a semi-metal. Over here on the right, there's some other interesting information. There's the various models that help us understand how atoms work. But atoms do not actually look like this. Nowadays, this is the best model we have for what all the shells actually look like. And then finally, I'm going to show you over here on the left, I have a little table which shows the original 12 elements that were known in ancient times. And this explains why sometimes the symbol doesn't match with the English name. So for example, the atomic symbol for iron is Fe. So sometimes people wonder, well, why is that? Well, that is because originally in Latin, this element was known as ferrum. So the Fe stands for ferrum, even though we call it iron. Or another example would be Au, which is the symbol for gold. That's because in Roman times they called gold aurum, and so Au stands for aurum. In 1807, there were two elements that were isolated and given alternative Latin names. That's why Na stands for sodium, because its alternative name in Latin is natrium. Potassium can also be known as kalium, and that's why we have K for potassium. So that's my alternative periodic table and why I've arranged the elements like this. I tried not to get too technical, but basically the theory is that this arrangement helps highlight the blocks. And again, those blocks have a relationship with how the electrons are arranged into subshells in the atom. So by looking at the periodic table this way, you kind of get to see the structure of how atoms are formed, and as atoms get larger, how those electrons are arranged. I also find that this symmetrical design also looks nice, and yeah, I just thought I'd do something different in terms of the periodic table. If you want a copy of this as a poster, it's available on my website, usefulcharts.com. Thanks for watching.